previous lesson, we considered the quantum Fourier transform and stopped on conversation at an ambiguous situation. On the one hand, we obtained a very interesting result, since the quantum Fourier transform turned out to be much faster than the classical one. On the other hand, it is impossible to use it for its intended purpose, for example, for analyzing and processing data, due to the reduction of quantum states and the problems associated with it. However, as we mentioned earlier, the goal of Fourier transform is to move from one type of functions to another, in which the solution of a particular problem becomes easier. In addition, we have already seen with the examples of the Deutsch and Deutsch-Jozsa algorithms that the essence of the quantum computations lies not in determining some particular result for a certain function, but in establishing the global properties of this function. For example, in the Deutsch problem, we did not find the individual values of the function f, but consider the whole superposition of the values of this function using quantum parallelism and interference, and then made conclusions about whether the function f is constant or balanced. And in this regard, the quantum Fourier transform is a kind of tool that allows us to collect information of interest from a certain initial set of qubit states, which generally is a fairly large superposition, to study important properties from this global information. In fact, this is very similar to the usual Fourier transform when we have a continuous time function or the sum of such functions, and then we want to say something about their spectral properties. So, let's take a closer look at ways in which we can use a quantum Fourier transform to determine the eigenvalues of some unitary operator. Consider the problem statement. Suppose we have a unitary operator U with its eigenstate U. Since the operator is unitary and does not change the normalization of the state vector U, the eigenvalues of such an operator can be represented as a complex exponent with argument 2 pi I multiplied by some phase phi, where I is an imaginary unit. Thus, each eigenvalue of the operator U is determined only by the phi phase, and we want to find that phase using the following procedure. To determine the eigenvalue, we'll use controlled quantum logic gates capable of preparing the state U and performing the operation U to the power 2 to the power j for the whole non-negative j. Our procedure will occur in two steps. In each of the steps, we will use two registers. The scheme of the first step is presented on the slide. The first register, or data register, contains t qubits initially in the state 0. The number of qubits t defines how accurately we want to determine the eigenvalue. The second register, or value register, contains as many qubits as necessary to write the state u, and its initial state is u. Since this state is an eigenstate for the operator u, this state will not change in the process of calculating the phase. At the first step of calculations, we prepare an equiprobable superposition of all possible data register states using T-Hadamard transforms. Doing so, we apply the Hadamard transform to each separate qubit from the data register. Then, these qubits from the data register serves as control qubits for controlled logic elements, in which the corresponding degree of the operator U acts as a logical operation. Thus, for the last qubit, it is U to the power of 2 to the power of 0, that is just a zero transformation. For the qubit number t-1, this is u to the power 2 to the power 1, that is u squared, and etc. Let's see what state we get at the end of this first step after performing all the controlled logical operations.
Let's now consider the scheme that you see at the slide. And the point of interest is not the Hadamard elements, because it's very simple, but the unitary transformation u to the power of 2 multiplied by t minus 1. So, the state of the system after the 1u transformation is 1 over the square root of 2 0 state on the state of the second register plus 1, and here we have to perform the transformation u because the first register is in the state 1. So u to the power of 2t minus 1 on the state u. And we could write it in the explicit form. So it is 1 over the square root of 2, 0 u plus the state 1, e to the power of 2 pi I, 2 to the power of t minus 1, on the phase factor phi, and on the u state. So, if we consider all the unitary transformations that are shown on the scheme, we obtain 1 over 2 to the power of t in half, state 0 plus e to the power of 2 pi I, 2 to the power of t minus 1 on the phase phi, the state 1. The state of second qubit is 0 plus e to the power of 2 pi I to the power of 2 t minus 2 phi 1, and etc. In more convenient form, it could be written down as 1 divided by 2 to the power of 2 and a half, sum over the k from 0 to 2 to the power of 2t minus 1, e to the power of 2 pi I phi k on the state k.
So, we have obtained the state of the first register in the form of 1 divided by 2 in the power of t in half, the sum of k from 0 to k equal to 2 in the power of t minus 1. The resulting expression we have already considered in the previous lesson, and this is nothing but the result of the quantum Fourier transform of some initial state phi with wave. The wave in the notation appeared due to the fact that we determined the phase with some finite accuracy, which is defined by the number of the data register qubit t. Thus, in order to calculate the phase phi, or in our case phi with a wave, all we need is to perform the inverse quantum Fourier transform on the first register. As a result, we obtain the state of phi with a wave, which will be given by a set of qubits in the state of phi 1, phi 2, phi 3, and etc., phi t. This state will give a good estimation for phi and therefore for the eigenvalues of the unitary operator u, which corresponds to its eigenstate u. At the same time, qubits phi 1, phi 2, phi 3, and etc. phi t will be in the computational basis, that is, we can only measure them. Thus, we have obtained an algorithm that allows us to find with a good accuracy the eigenvalue of a certain unitary operator. And this algorithm, by analogy with a Fourier transform, will certainly be faster than any classical algorithm. However, this is not the end of the story. In the next lesson, we will see how one can solve an even more complex and interesting problem of numbers factorizing using the Fourier transform. That's all for now. Thanks for your attention.